Great.
Looking forward.
Yeah, thanks very much to the organizers for putting together this really fun workshop in this beautiful place. I'm extremely jet lagged, so I'll try my best to be coherent, but please interrupt with questions. So today I want to tell you about some work that we're just finishing up on different types of universality classes of Floquet thermalization. This was led by a really excellent student at Princeton who's going to be joining Stanford as a postdoc, Alan Morningstar. And we hope to post a preprint in the next week or so. Okay, so we'll hear a lot more about periodically driven Floquet systems next in Gil's overview talk tomorrow. But the setting I have in mind is a Hamiltonian, which is time dependent. And it's time dependent with some period t. It has some driving frequency omega. In these problems, it's customary to define this Floquet unitary operator, which is the time evolution operator over one period. And there's been a lot of work in trying to understand different types of regimes of Floquet thermalization, different types of Floquet phases of matter. So, it's generally said that in a Floquet system, if you have thermalization, the system simply thermalizes to a featureless infinite temperature state. And indeed, this is the maximum entropy state, which is consistent with the absence of any conservation laws in the system. Okay, so if you have a driven system, energy isn't conserved, and in that setting, everything just heats up to infinite temperature. Okay, so if you look at the eigen spectrum of this Floquet unitary operator, you can define Floquet eigenstates, and the Floquet phases define quasi-energies, which are only defined modulo omega, so they live on this circle. And then if you look at something like the eigenstate thermalization hypothesis, compute local observables in these Floquet eigenstates, they show no structure, okay, in this thermal phase. On the other hand, we have lots of examples of ways in which we can avoid this Floquet thermalization, for instance, by thinking of many-body localized systems, or by thinking of integrable Floquet systems, non-interacting Floquet systems. And in these settings, you can indeed get lots of different kinds of interesting Floquet phases, and there's a lot of beautiful work, okay? But all of this understanding is working in an asymptotic limit where you consider a finite driving frequency, and you take the limits of infinitely large system sizes and infinitely large times, okay? And this distinction between thermalizing Floquet systems and many-body localized or integrable Floquet systems is sharp in this limit, and then you can use these limits to define dynamical phases of matter, okay? The question that I want to address in this talk is to kind of expand this understanding just from these asymptotic limits, and actually to allow for a frequency which depends on the system size, and to consider a whole range of different dependencies, ranging from a very weak dependence of just logarithmically depending on system size. N will always refer to the number of degrees of freedom in my system. So these could be qubits. You can think of a system of qubits, n qubits. And I'll consider a range of frequencies ranging from very weakly dependent on n, like logarithmically in n, to something which actually scales extensively with n, okay? And this is, you might think that this is very unphysical. Of course, if I take my system size off to infinity, this is a frequency that's growing with system size. So that's not, that's asymptotically perhaps a bit odd. But this is certainly very relevant for all sorts of near-term simulators which are operating in finite size and finite time regimes and are very far from these asymptotic limits that have been studied in theory, okay? And it's also important for understanding all sorts of calculations on digital simulators, for instance, understanding Trotter errors for Hamiltonian simulation. So we're gonna, that's what we're going to do. And what we'll actually find is that we'll get qualitatively distinct thermalization regimes by allowing this frequency to vary. This will give us different types of Floquet thermal ensembles, even for this very weak dependence on system size. And these different types of thermalization regimes will be separated by crossovers. But by taking a particular, what's known as a non-standard thermodynamic limit, you can get these crossovers to become sharp dynamical phase transitions. Okay, so you're already familiar with this kind of non-standard thermodynamic limit. If you have an all-to-all interacting system, for instance, an SYK model, you know that in order to get a sensible, extensive thermodynamic energy, you need to scale down the couplings with N in a certain way. So this is already, you have some system, it has some interactions, and the interactions are scaled down with N for sensible thermodynamics. When you're talking about dynamics, you can do similar things, which is scale the frequencies or scale the couplings that enter in your problem with N in a certain way, and then take specific limits. I'll describe some limits of that kind. And by doing those, you can get sharp dynamical phase transitions. And the types of scalings that you consider could be very different for dynamics or thermodynamics, okay? And perhaps the most classic example of this is localization in a quantum dot, which was considered by AGKL. This is Altshuler, Geffen, Kamenev, Levitov in the 90s. And there they found that you had an all-to-all, you had a fermion in a disordered all-to-all interacting quantum dot. And by scaling down the hopping strength, you could get a sharp kind of dynamical phase transition between localized and not localized, okay? So I'll describe for you what these distinct thermalization regimes are. And finally, a motivation for this work is that finite size or finite time crossovers from thermal to non-thermal regimes have become increasingly important in many recent contexts, most notably in the context of many-body localization, okay? So understanding the universal properties of these finite size crossovers is an interesting problem in its own right, okay? And this universality may not be universality that's derived from some asymptotic phase transition, but then may nevertheless be universal features. For instance, we know that random matrix theory gives you a great degree of universality. We heard about some of that from Victor's talk. And likewise, you could get different universal properties that are not derived from a phase transition, but are nevertheless useful in thinking about a wide range of problems, okay? And I just want to expand on this motivation a little bit by talking about some recent work on MBL, okay? So in a paper that we posted last year, what we showed is that even in the one-dimensional many-body localized problem, where with minimal assumptions, we believe that there's a proof for the existence of an MBL phase, what we showed is that by considering a way to estimate where this kind of asymptotic phase transition, the asymptotic MBL phase transition is thought to be driven by a process, is thought to be driven by the proliferation of, by rare thermal bubbles that avalanche, that you have disorder fluctuations that can seed thermal bubbles. These are fluctuations, and then these thermal bubbles avalanche and take over the entire system. But this is a very slow kind of effect, and this asymptotic transition, which is thought to be driven by avalanches, we were able to give a lower bound for this transition at a disorder strength in a standard model that has been studied at a much, much larger disorder strength than had been thought before, okay, at some W of order 18, whereas previous estimates for this kind of finite size crossover into something that was believed to be the MBL transition seen in finite size numerics and finite time numerics was finite time experiments was thought to be a W of order 4, okay? So almost all the numerics and experiments that have been done in MBL are in fact probing a finite size or time crossover from a thermal to a non-thermal regime. And the universal properties of this crossover could be very, very different. Indeed, they're driven by resonances and not by avalanches. These could be very different from the asymptotic properties of the phase transition, which we understand through various RG treatments, okay? So there's this big separation there, and we have to really take steps in understanding what's going on here, okay? Likewise, if you look at numerics on MBL systems, what you'll find is a very clear mobility edge. Again, this is the same model I was telling you about, which sees this kind of apparent transition around 3 or 4, and it has this mobility edge because this axis here is an energy density, and you see this phase boundary depends on the energy density. But again, there are various arguments which say that asymptotically, this kind of mobility edge is disallowed due to thermal fluctuations. But the fact that you see this in in this finite size, finite time crossover regime just tells you that the thing that you're probing with your numerics is not really this asymptotic transition, okay? And finally, there's experiments, there's various nice experiments. This is a picture from a collaboration with Emmanuel Bloch, which again sees a very sharp crossover from something that looks thermalizing to not thermalizing in a 2D system. And this is an actual experiment, so now it's operating in regimes of finite time. And you see this kind of crossover, but again, there are arguments due to avalanches which tell you that an asymptotic phase transition in 2 dimensions is disallowed for MBL, okay? So there are all sorts of interesting contexts where you see crossovers from thermal to non-thermal behavior in finite size and finite time regimes, and an understanding of those crossovers and the universal properties thereof is still there's almost no work on it because everything has been focused on trying to understand some kind of asymptotic phase transitions, but what we're seeing now is very far from that, okay? So that's the motivation, and the MBL crossover is a much harder problem. There's lots of interesting things that happen here. So to start, we're going to tackle the simpler problem of Floquet thermalization, and we're going to probe these different types of thermalization regimes that are accessible, that are available at finite sizes, and crossovers between them, okay? So since this is a pretty short talk, let me give you a preview of the results, and then we can flesh them out. So what we'll find is that there are distinct, even for this weak scaling of omega with system size, we'll find distinct Floquet ensembles, and these could correspond to an average energy density that may still be consistent with infinite temperature. In fact, when omega scales this weakly, they do, but the distributions of energy look very, very different, okay? So infinite temperature, featureless infinite temperature, just means that every state is occupied with equal probability. But what we instead get is that even for this very weak scaling of omega, you end up with distributions that populate a well-defined ladder of energies spaced by omega, okay? And the full distribution, even if the average agrees, the full distribution actually looks qualitatively distinct from a featureless infinite temperature state. Then I'll show you a full finite size Floquet phase diagram with many different kinds of heating regimes, which are distinguished by the properties of Floquet resonances. I'll tell you what these resonances are. And one key thing is that this phase diagram depends strongly on the quasi-energies theta n. Okay, so again, these quasi-energies are defined by looking at the eigenvalues of the Floquet operator, and usually in numerics that people do, you just say that, okay, it's a Floquet system. Again, there's no, in the thermalizing phase, there's no dependence on quasi-energy, so you compute some property of the Floquet spectrum and just average across the entire spectrum, okay? But if you do that, then a lot of the physics that I'm going to talk about will just get washed out or blurred because there's actually an interesting dependence on this quasi-energy, okay? And there's different behaviors as a function of that. And finally, I'll tell you a way to use this kind of analysis to dynamically generate, and this can be done in an experimentally feasible way, to dynamically generate Schrodinger cat states of different temperatures. Okay, so Schrodinger cat states are global superposition states. So usually you think of something like an all up plus all down state. People want to prepare cat states in the lab for all sorts of reasons. Here, what you'll end up with is Schrodinger cat states between a state at some positive temperature T1, for instance, and a different state at a negative temperature minus T, okay? So there are different temperatures, there are different energy densities, they're macroscopically different, and by starting with some simple product state that you can make in the lab, you can dynamically generate this kind of Schrodinger cat state of temperature, okay? So any questions in the setup? All right. Yeah. I'm going to talk about this, just preview of results. Okay, yeah, okay. Good. All right, so let me give a very brief review of Floquet thermalization and heating. So we have this periodically driven Hamiltonian. You can write it as some time-averaged piece. We're going to, in this system, in this problem, we're not going to talk about MBL or any of that. So this is assumed to be a thermal time-independent Hamiltonian with some time-dependent driving piece. This V of t is a local drive. It's a sum of local terms. And it has this periodic time dependence. I have my Floquet unitary, and I can use that to just mathematically define this H Floquet. Okay? This H Floquet can be constructed in a high-frequency Magnus expansion, of which the leading term is this time-averaged piece. However, this expansion is only convergent when omega scales with the many-body bandwidth of the system. So in general, this is not a convergent expansion, and H Floquet is a very nasty non-local object. Okay? It's just the logarithm of this Floquet unitary operator. But in what's known as a pre-thermal regime, where you can arrange your scales so that your frequency omega is much, much bigger than some local energy scale in the problem. So this could be, that's defined as omega naught. This could be the scale, for instance, of couplings that exist in H naught. So when omega is much, much bigger than omega naught, but still much smaller than the full many-body bandwidth, what you can do is you can truncate this Floquet Magnus expansion to some most optimal quasi-local Hamiltonian, which we'll call H effective. And this H effective describes the dynamics for very long time scales, which scale exponentially with omega over omega naught. Okay, so this is still an order 1 time scale, but it's still large. And this approximation of U Floquet with this effective Hamiltonian, this effective quasi-local Hamiltonian obtained by truncating this Magnus expansion, is not exact. Okay, and in particular, this H effective does have an extensive conserved energy E effective. It's just a well-defined quasi-local Hamiltonian. But we know that U Floquet only conserves quasi-energy modulo omega and not energy. Okay, so the difference between U Floquet and its approximation as e to the minus I H effective t is indeed exactly this heating process, which violates conservation of E effective. Okay, and it's driven by connecting different states in H effective, which differ in energy by omega. And this heating is only visible on times, strongly visible on times that are greater than this pre-thermal time scale, and it's reflected in various non-perturbative, non-local corrections to H effective, which are included in H Floquet. Okay, so that's just a review. So now already we can use this to see how you can get these distinct infinite temperature ensembles. So let's work in this pre-thermal regime where omega is much, much bigger than this local energy scale in the problem, but it's much smaller than the system size or the number of degrees of freedom n. Okay? So here you have a heating rate for the system which scales as e to the minus omega over omega naught times n. Okay, so this exponential dependence is coming from pre-thermalization. The idea is that you have a local energy scale which is omega naught, and your frequency is omega. So to absorb one photon from the drive, you have to make many local rearrangements, order omega over omega naught local rearrangements. So this is a high order process, which gives you this exponential suppression. And the overall factor of n is just coming from the fact that this local heating process is happening everywhere in your system because your drive is a sum of local terms. So on net, your heating rate is n times e to the minus omega over omega naught. Okay? So because of this low heating, the eigenstates of the Floquet unitary are not just going to be the eigenstates of H effective. Okay? If your frequency was much bigger than the bandwidth, then the eigenstates of H effective and the eigenstates of U Floquet more or less agree. But when this is not true, then the eigenstates of U Floquet are not the eigenstates of H effective, but they're supported on a ladder of energies spaced by omega. Okay? Because as a result of this drive, you're connecting energies that differ by omega. But each of the states in the ladder has a width which is set by this heating rate. Okay? You can think of starting with some state at some energy, but that state has some finite decay probability into all these states at these different energies, which is coming from the matrix elements of coupling to those energies, which is exactly what's setting this kind of heating rate. Okay? So So you have a gamma, you have this ladder of energies which have width gamma and are spaced in by frequency omega. Okay, but now notice that already from this we see that when this line width is much less than omega, that is when omega over omega naught is much bigger than log n. So it's very weak. Okay, the Magnus expansion is horribly non-convergent at this point because that requires omega scaling with n, but omega's only scaling is log n here. So already for this very weak omega dependence, we find that this distribution of energies, just 5 minutes? Oh, okay. Oh, I see. Okay, is very non-uniform. Okay, and this looks very different. So this is the density of states for H effective, and you see that you populate a ladder of energies here spaced by omega, and this is very different from this featureless infinite temperature state, which exists when this line broadening is comparable to omega, where each state is occupied in proportion to its density of states. Okay, so you can define a scaled frequency by rescaling omega with log n, and then there's a transition at this scaled frequency being of order 1 and going from this kind of featured infinite temperature ensemble. The average, all these different peaks still have the same energy density, so they're still at the same temperature, so this is still dominated by infinite temperature, but the distribution looks very different, okay? And if you look at gamma over omega, this has an n dependence which diverges with n on one side of the transition and decays on the other side. So you can see this sharpens up in the large n limit into an actual dynamical transition, okay? Now let's consider the case when omega is extensive and scales with n. So now you can write omega as n times some intensive energy difference. And we're going to now make resonances between states at different energy densities, okay? Because omega is itself extensive. So if you're connecting states at different, at multiples of omega, these have different energy densities. And to start, let's consider the hybridization between two states at minus omega over 2 and omega over 2, or between states at this energy density corresponding to minus omega over 2 and omega over 2, okay? And if you fixed this, if you're looking at multiples of omega over 2, then what you find is that this quasi-energy that you're looking at is fixed at theta equals pi, okay? So that's a given quasi-energy on this quasi-energy circle, and those are the states that you want to connect in resonance. Now you can do, again, a golden rule type analysis where you look at the matrix element, you consider one level at minus omega over 2, and you ask about the process that hybridizes this level with this continuum of states that it sees at plus omega over 2, okay? And whether or not it sees a continuum of states, that is whether or not you can apply Fermi's golden rule, is justified by comparing the matrix element for coupling between these states with the density of states or the inverse level spacing at this other energy. Okay, so this gives you a simple condition which when the matrix element dominates over the level spacing, you'll end up with Floquet eigenstates that are equally populated at between minus omega over 2 and plus omega over 2, versus when the matrix element is small compared to the inverse level spacing, you'll end up with these energy localized eigenstates, okay? And now we are talking about extensive frequencies. So this condition here, this crossover between this hybridized or Floquet thermal regime and this energy localized phase exponentially sharpens to a phase transition when omega over n are taken to infinity, but with omega divided by n fixed, okay? So this gives us a new type of Floquet ETH that we should be considering, which is this equal population of states at temperatures T and minus T corresponding to energies at minus omega over 2 and omega over 2, but this is not infinite temperature, okay? Because this infinite temperature would be an average energy there, but these are at temperatures plus T and minus T, which are distinct from infinite temperature, okay? So that was when, yeah? Mm-hmm. The most optimal H effective from the Magnus expansion, exactly. Yeah. So this was, when you were looking at states separated by omega symmetrically around the density of states of E effective, that corresponds to a specific quasi-energy, theta equals pi. But more generally, if you look at different quasi-energies, then you're going to consider hybridizations of states that are still separated by omega, but now they're not separated symmetrically, okay? So in particular, the density of states at energy density E1 is not going to be the same as the density of states at energy density E2, and you're going to have to look at all sorts of different, so the condition for whether some state that starts off at E1 ends up populating this ladder between E1 and E2. This is just a two-zone approximation. Of course, you could have all sorts of other things that continue on. Whether some state that starts off at E1 will populate this ladder in proportion to the density of states is given by this condition, which again cares about the matrix element in going from E1 to E2 and the density of states between them, okay? So in this wedge here, which is what we call the two-way heating phase, you can start with something at a low temperature and it'll end up acquiring weight on this high temperature state. But there's also this small reverse heating process where you can start with a high temperature state, and this won't really be visible, but it will acquire some weight to get to the correct Floquet thermal ensemble on this lower temperature state at E1, which is separated by omega from it, okay? So that's this two-way heating regime. But then there's a weaker condition for just one-way heating, which is when you get this forward heating process, but you don't have reverse heating, okay? So this is not allowed. If you start with some high temperature state, it just remains a high temperature state, okay? And that defines these other wedges here. When you have theta equals pi, you don't have this distinction between one-way and two-way because the density of states at E1 and E2 are the same, and that's this particular cut through the phase diagram where the blue and red curves meet, okay? And if you increase frequency even more, you get to the point, this is the energy localized phase where there are no resonances altogether. Your Floquet eigenstates are completely localized. And in the middle there, you can get rare isolated resonances, but not this kind of two-way or one-way heating process, okay? So this phase diagram is made as a function of the two energy densities you're mixing, E1 and E2. The frequency is obtained by taking cuts E2 minus E1. The average energy density is obtained by taking the average. And you see from this diagram that there is a strong quasi-energy dependence because the quasi-energy is set by what E1 and E2 are doing. Okay, and each of these crossovers, again, becomes a sharp phase transition in this non-standard limit. And this is the last slide. What you can do, and this is an actual numerical simulation that can be done in a lab like Emanuel Bloch's lab, is you can start with some generic initial states. So I said all this in terms of H effective, but H effective is, of course, extremely difficult to both calculate and prepare. But you can start with some generic product state, which will have some square root of n uncertainty, which will add to the width of these levels. And you can't measure H effective, but you can measure some proxy of it. And by looking, for instance, some total field, and then by looking at the full counting statistics or the full distribution of this quantity that you're measuring, which you can do for something like a field, what you can find is that if you start with just some simple product state, in time, that product state will evolve to, again, occupy this full ladder of different energies, which are superposition states or cat states between different temperatures, and this can be experimentally seen and measured. Okay, so that's a summary slide, which just recapitulates those points. And thanks for your attention.